Okay, so the next concept we're going to talk about, and I guess the last one of this week, is going to be second order ordinary differential equations. So we talked about first order in the last couple of videos. And so first order just have a first derivative and its function. Second order equations are similar. They involve the second derivative. But things can be a function of the second derivative, the first derivative, and the function itself. So like the damped spring mass here has y double dot, or the second derivative of y. It has y dot, the first derivative of y, and it has y itself. And then it has time. So it gets a little bit more complicated. But again, for physical equations, these are common. So some examples are, so you have some governing equations for different physics problems. You have a swinging pendulum, right, which ends up being a sine and cosine function. And you get that from this swinging pendulum equation right here. Right, so it's periodic, and the solution of this, even though it doesn't look like it, is like a sine or cosine. The undamped spring mass is like you have a spring connected to a mass, the basic physics 1 problem, and you let it go, and it just kind of oscillates back and forth, back and forth. The damped spring mass problem is a similar one where it goes back and forth, but the dampening is this C times y dot, and what that ends up doing is it's like some sort of friction or air resistance where it'll end up oscillating less and less until it just basically stops, right? And so, but that is just described by this second order differential equation here. And that's exactly what the solution ends up being. It ends up being a sine or cosine function, but then you also have like an exponential decay attached to it, where the amplitude of that sine or cosine function gets smaller and smaller until it basically just stops. And on the electrical side, LC circuits, if you're thinking of circuits, the LC circuits end up having a periodic response, a second order response as well. And so as always, how do you go to solve these problems? Well, I'm going to just show you, I'm not going to show you a numeric strategy you can hard code yourself because they get more complicated for higher order equations. But you can still use the ode45 function here. You can use the same thing. It's just going to be a little bit more complicated to set up this function. And I'll show you why in a moment. And so, as usual, I want you to isolate the highest order derivative, isolate the second derivative. And so, like in this case, you would get theta double dot by itself. So you'd subtract g theta over and divide by L, and that's your d squared y, or d squared theta over dt squared is equal to negative g theta over L, right? And so you have to solve for the highest order derivative, and that way you can actually set it up to be plugged into your equation. And so I'm actually going to do that problem. Is for this, at the top, I have a swinging pendulum. It's L d squared theta over dt squared plus g theta equals 0. And this is what you get when you just solve for d squared theta over dt squared. And in this case, for second order equations, you have to have now two initial conditions, one for theta and one for the derivative of theta. Because second order equations, you have both your function and its derivative as unknown, so you need basically two initial conditions for it. And you can also think about it like if you've done any integrals or anything, it's you're taking the integral twice effectively, right? And so if you take the integral twice, you end up having to have two initial conditions to solve that problem. And that's kind of the reason. And so now I have this very simple equation here. But what I have to do is, in order to use ode45, you end up having to convert to something called state variable form. You have to turn this second order equation into a system of first order equations. So this is where it gets complicated. So I'm going to try something new. I don't really have a way that I can use a tablet to write all this stuff out for you. But let's say I want to create a state variable form for this. Let me just explain it step by step. I have my equation already isolated, right? I have this here. And so I have to create state variables for it. My end goal is going to be to create a matrix of solutions that are going to be this x1 dot and x2 dot. So I'm going to set my theta equal to x1 dot as my start. And so I have to create this kind of this separate form of equations because it gets a little complicated. And so I want to set my first step is going to be to set x1 is going to be equal to theta. That's my first step. That's what I have to do first. I might just end up copying and pasting this over there. And the reason I have to do that is because that's my first variable. That's the variable in question, right? That's the solution that I'm looking for. And so the solution of this equation will end up giving me what x1 is, or what theta is. And so then my next formula is you take the derivative of both of these, of both sides, right? So you take the derivative of both sides and you get x1 dot, you get your first differential equation. Your x1 dot is equal to theta dot. And here's where you have to bring your second variable in, because the whole point is to get a system of two equations, because then I could take the derivative of this again and get x1 double dot is equal to theta double dot. But that just ends up being the same equation here. I only have one variable. But what I want to do is I want to end up having two variables in this system of equations. And so what I'm going to do here is I'm going to set this equal to, oh, I hate word equation editor sometimes. This is going to be equal to x2. So I'm going to create my new variable, and x2 is equal to theta dot. And so I've created my new variable. The derivative of the function is my new variable. So hopefully you're following me at this point. And now my second differential equation is going to be my x2 is equal to theta double dot. x2 dot is equal to theta double dot. So if you take the derivative of this equation now, gosh, I hate word equation editor. You take the derivative of this equation and you get x2 dot, which x2 is equal to theta dot, is equal to the second derivative of theta. But my second derivative of theta is this equation here. So I can copy and paste it over here. That's equal to negative g over L times theta. But what? But wait a second. I just created this new system of equations, and my theta is now equal to x1. And so my two equations end up being that I'm going to plug into MATLAB. And I know this is a complicated way to get there, but you have to do it. Use ode45. Is your two setup of equations that I'm going to put into MATLAB are these two right there. That x1 dot is equal to x2, and x2 dot is going to be equal to negative g over L times x1. And like I said, I don't really want to explain it much more past the reason that you just have to do it. You have to set up a system of first-order equations in order to solve a second-order equation, because effectively ode45 and all these solvers use a first-order solver effectively. And so you have to kind of set it up this way. And you could realistically do the same thing for the Euler solver, but that's too complicated for this problem. I could, with these orders, with these system of two first-order differential equations, I could do an Euler solver for both. It's just going to get more complicated. And so the way that you plug these into ode45 is you represent x1 and x2. So I'm just going to copy this over here, even though you can read it. X1 you plug in as x of 1, and x2 you plug in as x of 2. And so hopefully as I go through and set up this equation, it will make more sense in MATLAB. And so now I've shown you how to derive this. And this is the same logic you're going to use every time. First you set your function, in this case theta, equal to x1. Take the derivative of it, and that's equal to x2. So that's your first equation. Then you take the derivative of x2 is equal to theta double dot, and now that since you've solved for theta double dot, you plug it in. And so these end up being your two equations you use. And so now let's show you, all right, so that's all well and good. How do I implement this in MATLAB? Because that's what we really care about in this class, right? And so it's going to end up looking like a similar format as when we used ode45 before. And so I can set up the equation much like I did before. Is going to be equal to ode45. Remember, my first one is going to be some function which I haven't created yet. I'm going to end up calling it pendulum. My t span is going to be, I didn't give it to you, but I'll just say it's going to go from 0 to 5 seconds. And now I have to give it, remember, I have two initial conditions now. And so I've got to think about it. How do I set these up? Well, the first one, theta of 1 is going to be my actual theta value. So I put theta of 1, my actual function initial condition, my theta initial condition here is 0.5 radians. So I'm going to put 0.5. And then my x2 is equal to theta dot, right? And so that I need an initial condition for as well, and that's going to be equal to 0 radians per second. All right, so that's my equation. That's going to be what actually solves this equation. But the meat of this problem is setting up my problem in this form right here. And so let me create my function that I'm going to use in ode45. And it's going to just be x dot is equal to pendulum t comma x. Or in this case, I could do theta dot. I'll be more consistent. Theta. Actually, no, it's x because I created my x's, didn't I? So my x is going to be, remember, x of 1 is going to be equal to x1 in these equations. X of 2 is going to be equal to x2 in these equations. And I'll show you what I mean here. And so I need to define g and L. This is some numbers. G is going to be equal to 9.81, the gravity constant, that's what it means. Then L is just going to be equal to 1. The length of my pendulum is 1. Okay, so now I go in and actually plug in these equations. And so my x1 dot, and I can just type these out here, x1 dot is equal to x of 2. Right? That's exactly what I came up with here. Remember, you plug x2 is the second value of x, the second column of x, basically. So that's my first equation. Remember, I said these are the two equations, my two differential equations that I'm going to use. And then my x2 dot is going to be equal to negative g over L times x of 1. Because again, x of 1 is going to be equal to x1 right here. And that's the reason I had to solve for it in these forms, because what I needed are these two differential equations, x1 dot and x2 dot. And so now I'm going to put these into my x dot output. And you have to put them in a very specific way. And this is just the way that MATLAB has to have it to solve them, is you need x1 dot and then in the first row, and then x2 dot in the second row. And so this is basically using the setup of these two. And so this will allow you to set up so that my theta initial solution is my first row of values is going to be, or I think it ends up being my first column of values ends up being the x1 dot or x1 or equal to theta. My first column will be theta. My second column will be theta dot. And so that's just the way you have to set up these equations. So that's the other key is you have to set them up eventually so that they're both x1 dot and x2 dot are in an array. The first row needs to be x1 dot. The second row needs to be x2 dot. And so then I can plot it, right? And so I have the solution. Let's just look at what my solution ends up being. Before I go to plot it, let's just run it, make sure it works. Great. And you can look, and this ends up does indeed being two columns. The first one is theta. The first column is theta. The second column is theta dot. And then t ends up being from 0 to 5. Great. So it ended up working exactly the way I thought, which is a good sanity check for myself. And so let me go plot these. And so I'm going to do fig1 is equal to figure. I'm going to change the color to be white. Okay, and so now I can go ahead and plot t theta of, I want the first column, remember, was my theta values. And so that's pulling out all the rows, the first column, and this is going to be plot theta. Let's see what that ends up looking like. All right, and so it's a cosine wave, which makes sense, right? If you pull the pendulum out, it ends up going back and forth, right? Back and forth, back and forth. And what we're doing is this equation is coming up with the angle, effectively, of that bar, the pendulum bar, as it goes back and forth. And so it makes sense that it's a cosine wave or a sine wave, because it starts at some position, goes to the negative of that position, the other side, right, of the pendulum, and then swings back and forth. And this would just keep going to infinity. Let's see what theta dot looks like. So let me hold on. And I'm going to plot t and then theta 2, which that is equal to theta dot. And so the second one is this sine wave here. And if you look, you should pay attention and make sure your initial conditions worked. So this blue curve is my theta, is the angle of it. And then the orange curve, or this red curve, is theta dot, or the velocity, basically how fast it's moving. And so that's going to change as well as a sine wave. And so let's pay attention to our initial conditions. My initial condition for theta was 0.5. Look, it did that. That's good. And that's another way you can check which one's which. And then my initial condition for my my theta dot is 0, which basically means that, right, it starts at rest. So like I basically took this pendulum, held it out to some value, and it stopped at the start and then let go of it. And so it starts at rest. So it'll stop on the other side, right? Like you throw a ball up in the air, it stops at the very top. The pendulum, much in the same way, it slows down until it stops at my maximum displacement, right? My maximum displacement here is the same as my theta dot of 0 as my maximum theta, and then it'll keep going. So this looks perfectly fine. It looks like it worked fine. So that kind of gives me credence that, all right, so my state variable form worked. Wonderful. And so now here's another example that I wanted to do real quick. Is I have a spring mass dampener system. And so I need to solve for my highest order derivative. So this is going to end up being all of this. So if I divide by m, all of this divided by m is going to be my my highest order derivative here. So I go to the next slide and let me full screen it. I end up getting, oh, I think I messed this guy up a little bit. Let's go over here. I need to divide by m in this equation. I think I might have assumed m is 1, but that's fine. I'm going to actually just put it in here. So this is my equation there. And so let me full screen it, and I'll walk you through these steps again. So I'm going to go through this same method, converting it to state variable form, as I did for the pendulum problem. And so I start off with this equation here, negative cy dot minus ky over m. And I'm going to convert it to state variable form. So my first step is my lowest function, my lowest order, or y, is going to be set equal to x1. So x1 equals y, the actual variable I'm looking to solve for. And then my second equation, and then my second variable is going to be the derivative of that. So my first differential equation ends up being I take the derivative of this and get x1 dot is equal to y dot. Okay, that's fine. But then I set up my second variable is going to be equal to x2. So y dot is equal to x2. Then I take the derivative of that equation where x2 is equal to y double dot, but I know what my y double dot is. So let me walk you through this a little bit. So I know already that my first equation is going to be x1 dot. Oh, let me pull up my Word document on the side here. X1 dot is equal to y is equal to x2. Y dot is equal to x2. So that's my first differential equation ends up being that x1 dot is equal to x2. So now my second differential equation needs to be similar, right? It needs to be similar to this equation. It needs to be x2 dot is equal to something, right? And so in this case, it'll be my x2 dot is going to be equal to y double dot. But in this case, y double dot is equal to this right here. It's equal to this equation that I solved for at the very beginning. So x2 dot is equal to y double dot. So I plug in all of this. The nice thing about this, though, is I've already defined all of these variables, right? So if I go to the left here, y is equal to x1. So I can put in place of y, I can put x1. And then y dot I defined as x2. This is going to be x2. And so these end up being my system of differential equations that I'm going to plug in to ode45. And so to repeat, I started off by setting x1 equal to y, the variable of interest. I take the derivative of that and set it equal to x2, which ends up getting this right here. So the derivative of both sides ends up being x1 is equal to y dot, and I set that equal to x2. So my first differential equation, you take the y dot out of there, and you just say, all right, x1 is equal to x2. x1 dot is equal to x2. That's how I've defined it. And then you just take the derivative of again and get x2 dot is equal to y double dot, right? But y double dot I already know. I have my whole equation here, and so you plug that into your equation, and then you plug that into your equation and plug in, and you get you still have y dot and y in your equation, but you know what those are in terms of x1 and x2, because your end goal is to get two equations that only have x1 and x2 in them. Because when you plug these into MATLAB, x2 is going to be x of 2, and x1 is going to be x of 1. Because that's what down here, I even said it. You need to have those values for ode45. And so my final equations end up being these two right here. And so I can actually just use those right here. And so let's go ahead and solve that problem. I'm just going to, and I gave that m is equal to 1, c is equal to 2, k is equal to 4. So let me actually pull that up and add that in there real quick before I do anything else. And I can just plug these values into this equation. That'll be easier. So c is equal to 2, k is equal to 5, and m is equal to 1. And that was why I didn't include it, I think, in the rest of the solution, because it was already equal to 1. And so this is what I need to set up in my function file. So let's do that first. Start a little bit differently and set up my function x dot is equal to, I'll just do fun of t comma x. Remember, this is the format you have to use for ode45 and all the ODE solvers. You need to have time and your output as your inputs to this function. So t comma x is going to need to be my output for ode45 of at fun. My t span, I don't know if I gave you, it's going to be 0 to 6 seconds. I probably did. And then I gave you my initial conditions are, for y0 is going to be 1, for y is going to be 1, for y dot is going to be 0. Again, this output is exactly what you need to have your input be for x dot. And that's because these equations could have also been a function of time as well, but they're not. But you could have had some function of time in x2 dot as well. So you could have had like minus e to the negative t or something. You could have had that in there, and that would be fine. You could still plug that into the equation. And so now I'm going to just start typing out these equations. So I'm going to do x1 dot is going to be equal to x2, x of 2, right? That's what I said you have to do. Wherever there's an x2 or x1, you do x of 2 and x of 1, because those are literally going to be my values of this x right here. So x of 2 is my x derivative. It's going to be the second value of x, and that's going to be and that's kind of what I showed you in that output, is that there's going to be two columns where x of 1, the first column, is your actual y. X of 2, the second column, is your y dot. And so that's the reason you end up having to, wherever there's an x2, put it in parentheses, because that's literally saying that my second value of x is equal to x1 dot. And so then x2 dot is equal to x of, then this is where I plug in this problem. So negative 2 times x of 2 minus 5 times x of 1. Okay, and so then the last step is going to be that my x dot, so I still haven't created this output here, right? I need to create this output, and this is where I have to make sure that I include that I set this up entirely correctly. And so it's going to be in an array, and I'm going to have my first row be x of 2, my second row be, well, not x of 2. My first row is going to be x1 dot, whatever that ends up being. In this case, it is x of 2. My second row is x2 dot. Okay. And so now I'm really going to care about is plotting t, y, 1. So I'm just going to plot what y looks like, and it'll be a decaying parabola, basically, not a decaying parabola, the decaying sine function. And so let's see if this works. Oh, it didn't. What's the problem? Undefined variable y. Oh, it's because I said y, I meant x, because I defined this as x. What I could have done is I could have said y here to match the equation. And there you go. This is a decaying. So you have, it's a very strong decay because my dampening coefficient is pretty high. It's equal to 2. But as you can see, it starts off, this has the general form, oh, but I dragged it. The general form of a cosine function, much like the previous one, just the amplitude's getting smaller and smaller as it goes on. So if I decreased what this dampening coefficient was to 1, it should, see, it's even more pronounced here. It dampens it less, so the amplitude doesn't get as small throughout time, but it still does get smaller. And so that's how you would go and solve these second order equations using ode45. And so I have this code that I created up here, but what I want you to do is, this is going to be a more complicated one. So I'm kind of doing the opposite of what I normally do with these in-class problems. But I just showed you how to use ode45 to solve a second order problem. So what I want you to do is take the time for your third in-class problem, again, due Wednesday, is to solve Vanderpool's equation. It's a specific equation that it's a second order differential equation. So what I want you to do is use the method I just showed you to plot y of t, given this fairly complicated second order differential equation. And I wanted to do it over a range of t from 0 to 20. Mu is going to be equal to 1, so it stays pretty simple. And then here's your initial conditions. Y of 0 is 5, y dot of 0 is equal to 0. And so when you take some time, see if you can set it up. And what I'll probably do is I'm going to leave the Cauchy form here for you, this slide in here for you, just in case you're struggling with that. But try to do this on your own if you can. Because I want you to be able to set up this on your own, because you're going to have to do this on an exam eventually, and so you need to learn how to set this state variable or Cauchy form up on your own. So take some time, go through it, see if you can get this problem done, and as usual, I'm going to post solutions and me solving the problem, a video of it, once these are all turned in.